So next we discuss sedimentation. The colloidal particles settle down at the bottom of the container due to gravity at a very slow rate. The phenomenon is called sedimentation. It is used to calculate the mass of particle. What is sedimentation velocity and sedimentation mass? A particle of volume V and density ρ2 that is submerged in a fluid of density ρ1. The particle experiences a force Fg due to gravity taken to be positive in the downward direction. You can see here. Okay. So ρ2 is the density of the particle that is submerged in fluid of density ρ1. So this is the fluid here, ρ1, density ρ1. Okay, and this is the Fg force. Okay, so it acts downward. Okay, because of the gravity. At the same time, buoyant force Fb acts in the opposite direction, right? So buoyant force is acting on the opposite direction. Okay, so net force, it has to be balanced. Okay, so net force will be F net equals to Fg minus Fb. So we get V times ρ2 minus ρ1 times g, right? Now if ρ2 is greater than ρ1 and the particle is said to sediment. Okay, so when the density of the particle is higher than the density of the fluid, so the particle will sediment. If on the other hand ρ1 is greater than ρ2, then the particles will move upward, which is called creaming. So if ρ1 is greater than ρ2, so the particle will move towards upward direction. So we get creaming here. As the net velocity of the particle is increased, the viscous force Fv opposing its motion also increases. Once the forces acting on the particle balance, the particle experiences no further acceleration and a stationary state velocity is reached. That's what I discussed. Under stationary state conditions and for small velocities, the force of resistance is proportional to the stationary state velocity v. So stationary state velocity Fb, if we say Fb is a small f time v, where f is the friction factor. Since the net force and viscous force is equal in stationary condition, so we write it has to be balanced. So v times ρ2 minus ρ1 times g gives Fv, where v is the stationary settling velocity. Now for any particle moving in a fluid faces resistance by a force in the opposite direction. The force is given by Stokes law. Okay, this is the Stokes law. F is 6 pi eta rs times v, where eta is the viscosity. Okay, so for a spherical particle, the friction force is given by F is 6 pi eta times rs. So for a spherical particle, equation 3, this one becomes 4 by 3 pi r cube. So volume is 4 by 3 pi rs to the 3 ρ2 minus ρ1 times g. So it has to be equal to Fv. So F is this one, 6 pi eta. So 6 pi eta rs times v. Okay. So equation 6 may be solved for the stationary state sedimentation velocity. So stationary state sedimentation velocity is v is so if we rearrange this one, we get 2 by 9 rs square ρ2 minus ρ1 by eta times g. So if the radius of the particle, we can also calculate. So rs is, if we rearrange, rs is 9 eta v by 2 ρ2 minus ρ1 times g raised to the half. And mass of the particle, so mass is density time volume. So we mass equals to ρ2. ρ2 is the density of the particle and the volume of the particle is 4 by 3 pi rs to the 3. So we get 4 by 3 pi ρ2 times 9 v. So rs value now we are putting it here. So we get 9 eta v by 2 times ρ2 minus ρ1 times g raised to the 3 by 2. So next we discuss association colloid. These are substances which when dissolved in a medium behave as a normal electrolytes at low concentration but act as colloidal particles at higher concentration due to the formation of aggregated particles. This type of aggregate is called micelles. For example, sodium stearate we can take. The sodium stearate decomposes as stearate anion plus sodium Na plus sodium ion. In concentrated solution, the stearate ion aggregates to form colloid particles. These aggregates are called micelles. you need to remember that the formation of micelles takes place at a particular temperature is called Kraft temperature, and at a particular concentration called critical micellization concentration or CMC. Now, what is the mechanism of micelle formation? The molecules that form micelle consist of two domains, nonpolar hydrocarbon chain known as nonpolar tail. We have C17 H35. This is your nonpolar tail. It is hydrophobic or water repelling in nature. And next is polar group, which consists of CO minus. So CO minus is there. This is polar group. So polar ionic head group, right? It is hydrophilic or water attracting in nature. At CMC, the anions are pulled into the bulk of the solution and form a cluster in which the hydrocarbon chain from the interior and the ionic end are at the surface of the cluster. So you can see, so this is your hydrophilic end here or charged end here. This is water and this is the hydrophobic chain. Okay. So at CMC, the hydrocarbon chain form interior here, right, and ionic ends, okay, at the surface of the cluster, right. So in order to make favorable interaction with the water molecules. So ionic head of surfactant can be anionic or cationic. Here we are considering for stearate acid we are considering this anionic. Okay, head group is anionic. For example, cetyl trimethyl ammonium bromide, here you can see the head group is positively charged, cationic, and sodium lauryl sulfate, you can see the SO3O minus Na plus. So this is your, the head group is SO3O minus. So this is your anionic. Next we talk emulsions. Okay, what is the definition of emulsion? Emulsions are colloidal solution where both the dispersed phase and dispersion medium are liquids. The size of dispersed phase in emulsion is in between 1000 angstrom to 10,000 angstrom, which is larger than salts. So how do you prepare emulsion? It is prepared by mixing two immiscible liquids vigorously in a colloidal mill called homogenizer. As two liquids are immiscible, emulsions are very unstable. So an emulsifying agent or emulsifier is added to stabilize the emulsion. Emulsifier reduces the interfacial tension between two liquids, and emulsifier generally have long chain hydrophobic tail and an ionic head, for example RCO minus Na plus. Drop of oil gets surrounded by hydrocarbon chain and CO minus part remains in water. Thus, hydrophobic chain of emulsifier forms a film around each oil molecule. Consequently, interfacial tension between oil and water decreases. Example is in milk, casein molecule create a protective layer around fat molecule dispersed in water. So the opposite of emulsification is de-emulsification. So it is a process of decomposing the emulsion into its constituent liquids. There are several methods for demulsification like centrifugation, filtration, boiling and freezing. Examples are cream from milk is separated by centrifugation. What are the types of emulsions? Oil in water emulsion or aqueous emulsion. Oil acts as dispersed phase and water as dispersed medium. Example, milk, vanishing cream. Water in oil emulsion or oily emulsion. Water acts as dispersed phase and oil as dispersion medium. Example, butter, cold cream. What are the applications of emulsion? Concentrating the ores in metallurgy. For concentrating sulfide ore of a metal, froth flotation method is used. In medicine, cod liver oil, vitamin B complex are the examples of water in oil emulsion which are easily absorbed in intestine. Cleansing action of soap. Cleansing action of soap is based on the fact of formation of oil in water emulsion. Daily use, milk, butter, vanishing cream, cold cream, margarine are of daily use emulsions. Next we discuss some problems. What is the difference between low concentration solution of soap and high concentration solution of soap. Okay. Dilute or low concentration solution of soap dilute or low concentration of soap solution acts as simple electrolyte but a high concentration of solution of soap acts as colloidal solution. As it reaches critical micelle concentration, right? So it says that the for high concentration of solution of soap, since it reaches critical micelle concentration or CMC, so it acts as colloidal solution. Okay, whereas low dilute low concentration of soap solution acts as simple electrolyte. Okay. Next problem is what happens when a freshly precipitated FeOH whole thrice is shaken with a small amount of dilute solution of FeCl3. We just discussed in the class. Okay, so what will happen here is a reddish brown colloidal solution will be obtained. This is called, we just discussed, this is called peptidation. So, Fe3 plus ions from FeCl3 solution get absorbed in the on the surface of FeOH whole thrice. FeOH whole thrice precipitated and form positively charged colloidal solution. We just discussed while discussing peptidation. Okay, this one. So, the reaction will be the corresponding reaction will be the corresponding will be FeCl3, it decomposes into Fe3 plus 3Cl minus, right, and then FeOH3 we have plus Fe3 plus, so it gives FeOH whole thrice and then dot Fe3 plus. So, this is the colloidal solution. Okay. So, basically Fe3 plus ions of FeCl3, it get absorbed on the surface of FeOH whole thrice, okay, and form colloidal solution here, and the color will be reddish brown. Problem number 3 says, what will be the charge of the following colloidal particles? FeOH whole thrice. Okay, so FeOH whole thrice sol is, we just discussed it here. FeOH whole thrice sol is FeOH whole thrice sol is positively charged. Next is As2S3 sol. So As2S3 sol is negatively charged. These are all discussed in the class, okay. And third is colloidal silver solution, okay. So colloidal sol of silver. Okay, this is also negatively charged. Next we move to problem number 4. It says, explain how peptizing agent convert a precipitate into colloidal solution. Okay, this also we discussed, okay. So peptization process, or peptization is a process where a freshly prepared precipitate is converted into colloidal solution by adding a suitable peptizing agent. The suitable ion from the electrolyte on peptizing agent or peptiding agent is absorbed by the particles of precipitate giving it because it is an ion, so giving it a positively or negatively charged, right, giving it a positive or negative charges. These charged particles what will do? These charged particles will repel, right? Will repel each other and breaks the precipitation. Break the precipitation or precipitate rather, break the precipitate into colloidal particles. So, it forms a colloid. Example is, we just discussed small amount of FeCl3. So, as we discussed, FeCl3 gives Fe3 plus, okay, and then when it is added, okay. So, it gives, it absorbs on the precipitate, gives positively charged. So, these positively charged particles, they repel each other, okay, and then it breaks the precipitate, okay, and to form colloidal particles. Next problem is, why is colloidal gold is used for intramuscular injection? Okay, so colloidal gold is more effective due to its large surface area. And it is easily assimilated with the blood, which is, blood is a colloidal solution, which is colloidal itself. Okay. Since the colloidal gold is has more surface area, or large surface area, so it is easily assimilated with the blood. Blood itself is a colloidal, itself is a colloidal thing. Okay. Next, we discuss what is the reason for Brownian motion of colloidal particles. Okay. So, we just discussed this unbalanced bombardment of particles of dispersed phase by the molecules of dispersion medium, right, causes the Brownian motion. So, unbalanced bombardment of particles of dispersed phase by the molecules of dispersion medium causes Brownian motion of colloidal particles. Next problem is, a colloid is formed by adding FeCl3 in excess hot water. What will happen if excess NaCl is added to this colloid? So, when FeCl3 is added to excess hot water, so FeCl3, it gives positively charged. So, positively charged sol of we just discuss positively charged sol of hydrated Fe2O3 is formed, right, or is produced. is formed. On adding excess NaCl, the negatively charged, so it will form a surface and then the negatively charged Cl minus balance the positively charged salt, right? And coagulate positively charged colloids. Colloid solution. Okay. So the reaction is FeCl3 plus 3H2O gives FeOH whole thrice plus 3HCl. Now we have hot water, so heat is there. So we get basically Fe2O3 dot XH2O. Okay, and then we are adding FeCl3 we have, so we get Fe3 plus. So this is ferric oxide. Fe2O3 is ferric oxide. This is known as ferric oxide salt.